So we finished all the problems on worksheet 15 except the last one. So let's look at the last one. There are two cars moving at one moving at eastbound at 25 meters per second, and the other one moving at north at 20 meters per second. They collide at the intersection, and after collision they get stuck, and then they move together to the northeast at some angle. So we want to find the magnitude and direction of the final velocity after the collision. So this is two-dimensional problem because the cars are moving at two directions, okay, x and y direction. So in lab we saw the collision in one direction. So you pushed a cart along this direction and this direction, they collide and then they move back in the same direction. So this is one-dimensional problem, but here one car is moving this way and the other car is moving this way, so they collide and then they move at some angle. So there is motion in y direction and motion is in x direction. So this is two-dimensional problem. Okay. So when we deal with two-dimensional problem, we need to apply the conservation of momentum separately for x direction and y direction. So start with conservation of momentum in x direction. Exactly same kind of problem as in one dimension, but here we need to do this two times. Okay, conservation of momentum in x direction and then in y direction. Okay. So before collision, so conservation of momentum is before collision, or I should write total momentum before collision. I'll just write before. Before means before collision is equal to total momentum after. After collision. Same thing here, total momentum before collision, or sorry, before collision is equal to total momentum after collision. Okay. So this is along x direction, that's along y direction. Now here is the car. Here is the car. So let's call this one A, this one B. Okay, you can call it 1 and 2 or give some other name. So before collision, A is moving all along x direction, so it doesn't have any y component, and B is moving all along y direction, so it doesn't have any x component. So total momentum is momentum of A only, not that of B, because B doesn't have x component. So mass of A and velocity of A initial. Okay. If you want, you can also write mb v b I, but this is 0. There is no x direction, x component of this before collision. Total momentum after collision. After collision, it's combined mass. So ma plus mb, okay, and then along x direction, the velocity is v final x. Okay, so we are only talking about this direction. So they move along this direction although they move along this direction after the collision, but this momentum has part along this direction and part along this direction. So, we are talking about only this part, okay, x direction, that is x. Now, likewise here m a v a I plus m b v b I, but here this is moving all along x direction. So, it does not have y component. Okay. That means this must be 0. So, that is equal to, after collision it is combined m a plus m b, and after collision it moves along this direction, but we are talking about this part. Okay. So, this part y direction. So, along that part it is y final of y component, okay, y component of the final. So, does that make sense? Here it is all along x direction, here along y direction. Now, we need to solve these two equations to find v final and also angle. So, to find v f, what we need to do? You have this x component v final x, and you have v final y, and you want to find this v final. V final is the combination of these two. Okay. Any vector, you have a vector, you can break this vector into this x component and y component, and you can also combine these two to get this component, this vector. Okay. So, if you want, you can break down a vector into two components, or if you want, you can also combine the vectors. So, to break down, you write v cosine 30 degree theta, v sine theta. Okay, that is how you break it down. And to combine, how do you combine that? If you want to combine these two, what is the formula to combine the vectors? If you are applying force in this direction and force in this direction, the combined would be in between the two forces. Okay, if I am pulling this way and this way, it will move this way in between the two. So, what would be the combined vector, combination of the two? What formula do you use to combine the two vectors? You have a vector in this way, you have vector this way. The combination of these two would be between that. So, what is the formula to find the two, the combination of the two? We have done this several times before. Any guess? We have done lab on this, we have done several problems on this, and if you are taking physics 2, you will be doing the same thing in physics 2 also. And you have done this several times in trigonometry also. So, let me remind you how you did this in trigonometry. So, you have, let us call this Vx, this is Vy. You can write this Vy here also. Vx. So, this is the resultant V. How do you find that? You have this side and this side. How do you find this side? Yes, exactly. So, Pythagorean theorem, right? So, this perpendicular squared over this adjacent squared. Okay. So, if you can find this one and this one, then their resultant would be, using the Pythagorean theorem, Vfx squared plus Vfy squared. Okay, that will give you that. And how do you find the angle? This angle, theta is tan inverse of y component over x component. Okay, that's what we want to do. So let's find Vfx and Vfy. So we want to find this and that. So plug in the numbers. Mass of A. What is the mass of A? (1.5) times 10 to 3 kilogram. Velocity of A, 25 meters per second. What is the combined mass of A and B? 1.5 plus 2.5. 5 plus 2.5 times 10 to 3 kilogram, and then Vfx, and then do the math, you get Vfx. Okay, so I want you guys to do that and tell me a number. Do the same thing here. So mass of B is 2.5 times 10 to 3rd kg. VBI 20 meters per second. Combined mass is 1.5 plus 2.5 times 10 to 3 Vfy. So do the math and find Vfy. Give me a number. And then find Vfx squared plus Vfy squared, and then find theta, tan inverse Vfy over Vfx. So do that and tell me what numbers you got. Anyone has Vfx? (9.8). Say it loudly. 9.4. 9.4 meters per second. Okay. What did you get for Vfy? $12.5. Okay. 9.4 squared plus 12.5 squared, and take square root of that. See what you get. (15.6 meters per second). Okay, good. That's what I have. And theta. So what you get? 12.5 over 9.4. (53.1 degrees). Okay, that's good. Okay, so that's the velocity and direction of the car, or the combined mass of the two cars after collision. So they collide and then they move at 15.6 meters per second, 53 degrees from the x direction. So this is 53.1 degrees and 15.6 meters per second. Okay, so that's worksheet 15. Now we'll start new chapter, chapter 9. So there are three general types of motions. Okay, the first motion is called translational motion. Translational motion is where the objects move in straight direction like that. Okay, so you're walking on a road, that's the translational motion. You're driving on a road, that's the translational motion. Another type of motion is rotational motion. Rotational is you have an object, it rotates around some fixed axis. So that's the rotational motion. Okay, let's say you have a door. So this door is fixed at this pivot or hinge. You apply force, the door will rotate. Okay, so that's also the rotational motion. So in this chapter, we'll be talking about the rotational motion. And there is also third type of motion which we'll talk in the next chapter, which is vibrational motion. Vibrational motion is you drop a pendulum from some height, it will swing back and forth. That's the vibrational motion. Let's say you have a spring, you attach some mass to the spring and then pull the spring down and then let go. The spring will move back up and down. Okay, it will do up and down, up and down. That's the vibrational motion. So we'll talk about that next time, but now we'll talk about rotational motion. So this chapter is about rotational motion. Rotational motion is more or less same as translational motion. So in translational motion, we saw that in order to get some acceleration, we need force. Okay, force produces acceleration. This is for translational motion. But in case of rotation, to get the acceleration, we need something called torque. Okay, torque is angular counterpart of translational motion. So in order to rotate an object, you need something called torque. Torque is needed to rotate an object, let's say at rest. So what is torque? Torque is the rotational effect of a force. So if you apply some force to open the door and the force produces the rotation, then that rotational effect is called torque. Okay. So if I apply some force on some object and that force rotates the object, so that force is said to produce the torque or rotational effect. So rotational effect depends on three things. So let's say you have this door, you're looking from the top perspective. So you're looking at the door from the top perspective. You're applying some force Let's say one time you apply force this way, next time you apply force this way, next time you apply force this way. Oops. That's F3. Next time you apply force this way, you're applying exactly same amount of force but at different points. So which one will produce the maximum rotation on the door? You have 4 different forces. Yes, exactly. F1 will produce the maximum rotation. So that means the torque or the rotational effect produced by the force depends on first is how big your force is. Okay, how big the force is. Bigger the force, more is the rotation. Second is where you apply the force. For example, you apply the force at this point versus this point. From your experience, you can tell that this will produce more torque or more rotation. So it depends on distance between the force and this pivot or hinge. Okay, so this distance is called radial axis or R. Okay, so it depends on distance between the pivot. Pivot is the fixed point, and the point where you apply the force. And this distance is called radial distance. Now the third one is in which direction you apply the force. Okay, so you apply the force in this direction, like perpendicular to this radial axis, and in this direction. From your experience, you can say that this will produce more rotation, more rotational effect, more torque. So that means it depends on this angle between the radial axis and the force. Like if you apply force in this direction, either against the radial axis or in this direction, in the same direction as the radial axis, that will produce zero torque. If I push this way, it will rotate, but if I pull it this way, then it won't rotate, right? So it depends on angle, at what angle you apply the force. So those are the 3 things that affect the rotation. So we can combine those 3 into a single formula. So torque depends on force, distance, and sine of angle between force and distance. Okay. So torque is denoted by this Greek letter tau. Okay, this is small t, Greek letter, not small t, it's just some Greek letter tau. Force is F, distance is denoted by R, sine theta. Okay, that's the formula for torque. So torque is expressed in the unit of Newton meter, because it's the product of force and distance. Force is Newton, distance is meters. Okay. Now there are 2 ways you can find torque. So Let me show you both the ways. Both the ways are same, equivalent. So let's say there is a door or something that is fixed about an axis. Okay, so this fixed point is we call pivot. And let's say you're applying force in this direction. Okay, this is the radial axis. So the distance between the pivot and the point where you apply the force is r, and you want to find the torque, how much torque you produce. So the first way is break this force into two components. Okay, so this force has this component, vertical component, and this horizontal component. So this component, let's say this is angle theta. So this component is f cosine theta, and this component is f sine theta. So only this component will produce the rotation. This won't produce the rotation. Okay. If you pull this object in this direction, it won't produce the rotation. If you push it this way, it will produce the rotation. So this one does not produce rotation. This one produces rotation. Okay. So then torque would be given by this distance, radial distance, times the component that produces the torque. Okay. So this f sine theta. Okay. So that's one way. Again, split the force into two components, this component and that component, and see which component produces the rotation. So distance between the force and the pivot times that component gives us the torque. Second way, now let's consider the same example. Okay, so we have pivot here. We are applying force in this direction. Now this time, produce this force down like that. Okay. So just draw a longer line for the force. This line along which you apply the force is called line of action. So draw a long line of action. And from the pivot, draw a perpendicular line to that line of action. Okay, draw a perpendicular. You should need to be perpendicular. Oops. Let's see what happened. So this is this distance is r. Okay, this is theta. Then what should be this distance using the trigonometry? So here you have a triangle where this hypotenuse is r. What should be the perpendicular? Trigonometry rule. You have this triangle, this is r, this is theta. What should be that side? Trigonometry. Sine theta is opposite, which is question mark, over hypotenuse. So question mark is r sine theta, right? So this distance is r sine theta. So here in this way, this method, we will multiply this distance r sine theta with the force. Okay. So this is the second approach. So again, in second approach, you draw a longer line of action, line along the force, and then draw a perpendicular from this pivot to that point. Let me repeat that again so that you don't. So draw this line of action, first thing, which is along the force. Draw this perpendicular on that line of action from the pivot, and then see what that distance is, distance from this point to the line of action. So that distance times the force gives you the torque. Okay, that's the second way. First way, you have this force, divide this force into y component and x component, and then multiply this y component force by, multiply this by that distance. Okay, that's the second way, first way. So let's see examples that will clarify how you use that. So let's look at number 1 on worksheet 16. So those who are on Zoom, you can download worksheet 16 from Blackboard. Look at number 1. So we want to find torque. Torque is tau. So what's the distance between the force and the pivot, perpendicular distance between the force and pivot? So draw this force line of action. So that's the line of action. I don't know why it's doing that. So here is the force. Just draw, extend that line. So this is the line of action. This is pivot. So distance between the pivot and the line of action, what is that? 60 centimeters. Okay, and then force, multiply that by force, 55 Newton. Okay, we want this in meters, so 60 over 100 is 0.6 meter times 55. So that gives you the torque. That's one way. Another way is also same here in this case. Basically, you have this thing, rod, and that's the force. So you need to split the force into two components, x component and y component. You don't have x component here, everything is y component. So basically, torque is distance, this distance, radial distance, times y component of the force, which is itself the y component. So you get it gives you the same thing. Okay. So when it's perpendicular, it's pretty straightforward. You don't need to worry about the components. But now let's look at the second one. Second one is a bit complicated. So here you have this hinge or pivot. Here's the door. And you're applying force in this direction. So method 1, In method 1, torque is distance between the force and the pivot, this distance. So, what is that distance? Is it given? 60, yes, 60 centimeters, 0.6 meters. And then split this force into two components. So, this component and this component, y component and x component. So, this see which is their angle. So, this one does not give the angle. So, we do not have this angle in this case. So, that means we cannot use method 1. So, to use method 1 you need this angle. So, that you can find cosine 60 and then multiply this by not 60, sorry, theta. Oops, not cosine. So, this would be f cosine theta and this would be f sine theta. So, in method 1 you multiply this distance by the y component of the force. Okay. So, that is the torque, but we do not have angle. So, that means this is not useful. So, then use method 2. In method 2, so that is the force. Draw line of action. So, that is the line of action, and then draw perpendicular line on that line of action from the pivot. So, draw that. Okay. So, torque would be distance between the pivot and the line of action, okay, perpendicular distance, this distance, which is L. And then times force. Okay. So, L, how do you find L? Seems like there is angle missing here. Let me see my solution. I think we need angle to do this one. Yeah, so the question is missing the angle. So, this one, please write 40 degrees on this one. Okay, that figure is missing angle. No, this is the middle one, the number 1 part 2. Which one? Let me write it down here. So, the middle figure is what I am working on right now. So, let me draw it again. So, you have this some kind of object which is fixed at this point. Okay, and then you are applying the force in this direction. Okay. What I am saying is this question is missing angle. So, this should be 40 degrees. So, just add 40 degrees on this figure. Now, once we know this 40 degrees, we can actually use the first method also. So, this would be 40 degrees. So, 6 meters times force is 55, and then angle is 40 degrees. Okay. So, that will give you the torque, Newton meter. That is method 1. Now, let us look at the second method. So, draw line of action, just draw line or dot line along this force, that is the line of action, and then draw a perpendicular line from this pivot to that line of action. Okay. And then find this distance between the pivot and line of action. So, tell me what that line would be, what that distance would be. So, this is 0.6 centimeters or 0.6 meters. This is given. This is 40 degrees. Now, you guys tell me what that L is. Exactly. So, this L would be 0.6 sine 40 degrees. So, 0.6 sine 40 degrees, and then force is 55 Newton. Okay, you do that. These two should give the same answer. So, 0.6 times sine 40 times 55 Newton. What is that? .2 Newton meter. Okay. Let's look at number 2, or the third one first. I think the third one is pretty straightforward. You guys should be able to tell me the answer without actually doing the math. So, what would be the torque in the third case? You don't even need to do math, just from your common sense. 0, yeah, there won't be any rotation. So, torque is 0. Okay, let's look at number 2. So, there is a square okay, and then you are applying the force at 3 different points on that square. Applying force at this point, which is F1, you are applying force at this point, which is F2, and the pivot is at the center. So, that is the center, and then you are also applying force at this corner, F3, and then at that corner you are applying force at 45 degrees. So, you want to find the net torque. Okay. T net is torque due to the first force, torque due to the second force, torque due to the third force. So, let us find the torque due to the first force. So, there are 2 ways you can find the torque again. The easier way would be draw the line of action. So, that is the line of action. So, that is my line of action. Okay. And then draw perpendicular distance between the line of action and the pivot. So, that is the perpendicular distance. So, then torque would be that distance. Let us call that, what should I call that? Say R, okay, R times F1. So, what that distance is? So, the length of the square is 0.18. So, this length is 0.18. That means distance from the center to this side would be half of that. Okay. So, this would be 0.09 meters, and then the force F1 is 200 newtons. Okay. And then T2, do the same thing. So, draw a line of action So draw this line of action along the force, and then oops, I don't know why it's doing that. Okay. And then draw the perpendicular distance from the pivot to that line of action. So that's the perpendicular distance. Let's call that R2. So this torque would be that perpendicular distance times the force. Here R2 is again 0.09, half of the length of the side of the square, and then distance is, and then the force is 250. That's torque 2. Now torque 3. Again draw line of action. So this is the force. So draw this dashed line along that force. So I have hard time drawing. Let's see if I can use some kind of tool. So here is my line of action. Okay. And then draw perpendicular line from this pivot to that line of action. So that would be the perpendicular. And then you find this distance. Okay, so torque 3 would be that distance from pivot to the line of action. You guys tell me, what should this distance be? This is 0.09, this is 0.09, so I want to find this distance. How do I find that distance? (0.09 squared plus 0.09 squared, right? Just use the Pythagorean theorem. So square root of, let me first write the symbolic thing. So R3 F3, 0.09 squared plus 0.09 squared, square root of that, and the force is 150. That will give you T3 or torque 3. So what did you get for torque 1? Does anyone have answer for that? 18 Newton or Newton meter. Okay, and then torque 2, 22.5 Newton meter. Okay, and torque 3. Okay, that's good. Now, just like the force, torque is also a vector quantity. Okay? Vector quantity means we need to consider the sign. You cannot just add these 3 torques and get the net torque. Like you have these 2 forces, 20 Newton and 10 Newton. If I ask you what's the net force, you cannot just add 20 plus 10. That's not 30. That's 20 minus 10, right? You need to consider the sign. Just like that, here also, if the force produces clockwise torque, then you consider it to be negative. If the force produces counterclockwise torque, then you consider that to be positive. So if this is pivot, you apply the force here, will it produce the counterclockwise or clockwise rotation? Imagine you're applying force, yeah, so counterclockwise. So this will produce counterclockwise. So that means this one would be positive. T2, what's the rotation produced by force F2? It would be clockwise, right? This way. That means it's negative. How about F2? Counterclockwise, so it will try to rotate like that. So that's also positive. So that means T net is 18 Newton meter minus 22.5 Newton meter plus 13.5 Newton meter. Okay, so that would be, is that 14.5? You got 9? Okay, maybe I'm not correct here. Okay, so you got 9 Newton meter, and this positive means the net would be in counterclockwise. Okay, so we are out of time. I will stop here and then we'll continue this next time. Okay, someone got. Okay, so it seems like 19.1 is the T3. We'll check that later, next time maybe.